All right, so when the instructions are diagonalize, this is what you are to do. So this is your little cheat sheet right here, right? Cheat sheet, you won't get this. Well, I guess you get this because you can look at your notes. Forgot about that. All right, so get your cheat sheet. So this is the steps you need. First, I need to know what the eigenvalues are. So you need the characteristic polynomial, determinant equals 0, but can you notice this is a diagonal matrix, right? It's got a triangle of zeros, just the 1, 0. So I can easily pick out that the eigenvalues are 1 and negative 1. The eigenvalues are 1 and negative 1, the diagonal entries. So this is kind of an easy one. This one is not so much. Okay, so let's go and find the eigenvectors that go with each of the eigenvalues. So you're gonna have to be really clear so I can read your work, right? So say, okay, I'm gonna check out the eigenvalue of 1. So I'm solving ax equal 1x. So a minus, right, a, let me just go really slow so I don't make a mistake. 6, negative 1, subtract 1, 0, 0, 1, x equals 0, right? So subtract that over, ax minus x equals 0. So the matrix that I get here is 0, 0, 6, negative 2, x equals 0. All right, so then I'm going to row echelon this. So I get 1, negative 1/3, 0, 0, right? It's augmented. There it is. So I get x1 minus 1/3 x2 is 0. x1 is 1/3 x2. So my vector x will be 1/3. I can factor out the x2. I think you're good with this, right? So there's my eigenvector, right? My eigenvector would be 1/3 1, right? So you know that this means all linear combinations of this. So why don't I make it nicer? So why don't I multiply this by 3 and say 1, 3. So this is the eigenvector that goes with the eigenvalue of 1. The eigenvector, right? An eigenvector just means this is the vector that spans the solution set, right? That's why I can multiply it by 3. I'm talking about a vector that spans. Okay, so now let's go find the eigenvector that goes with the eigenvalue of negative 1. So I get ax equal negative x. So a plus I, right, plus 1, x equals 0. So let's go figure out what this gives us. So this gives us 2, 0, 6, 0, x equals 0, right? So if I augment that and row reduce, I'll get 1, 0, 0, 0, 0, 0, right? This is the augmented. So what do I get? I get x1 equals 0. What's going on there? So what does that mean? So my vector x is x1, x2, right? So x1 is 0. Where's x2? So sometimes this can be kind of tricky, but it's the simple stupid case. Well, x2 is free. It's missing, right? So my factor out my x2, I get 0, 1 as my eigenvector. So my eigenvector will be 0, 1. Okay, so now let's put together the p and the d. So the p is made up of the eigenvectors. The d is made up of the eigenvalues. So let's start with 1. So this eigenvalue of 1 I'm going to put here, and I'm making a diagonal matrix, and I'm going to put the eigenvector here. Then I'm going to put my eigenvalue of negative 1 on the diagonal, and then I'm going to put this eigenvector here. All right, so I'm just going to put, or I could have put my diagonal, or my eigenvalue of negative 1 and my d in my first entry, then this would be my p. I would put that vector there, and I could have put eigenvalue of 1 here, and then just put this vector here. So the p and the d are not unique, they just have to correspond. All right, if I get to a 3 by 3 matrix, I am always going to give you the eigenvalues because remember it's always going to be a cubic characteristic equation. So you won't ever have to go find the eigenvalues, only in a 2x2. So let's start off with lambda is 5. Okay, so that means I'm solving ax equal 5x. And so that means I'm taking the matrix A, 2, 2, negative 1, 1, 3, negative 1, negative 1, negative 2, 2, and I'm going to be subtracting off 5i, right? And that is going to be my a minus 5 I x equals 0, right? So I do the subtraction, I'll let you do that, and then put it into row echelon. So what I get is, I'm just putting the dotted lines in there so that you know I'm doing the row echelon with the augmented matrix. Okay, so what does this give me? This gives me x1 plus x3 is 0. x2 plus x3 is 0. So remember, you're making up your vector x1, x2, x3. So this gives me negative x3, and x3. So factoring out my x3, I get negative 1, negative 1, 1. So my eigenvector is negative 1, negative 1, 1 for lambda is 5. Okay, so now I'm moving on to lambda is 1. So again, I'm solving ax equal 1x. And so what I'm going to do is I'm going to take a minus 1, right? A minus the I matrix, x equaling 0. So it turns out to be, I'll let you go and do a little bit of work on your own, but I row echeloned it. There's my augmented matrix, row echeloned. So what does this give me? This gives me x1 plus 2x2 minus x3 is 0. So x1 is negative 2x2 plus x3. So again, remember I'm finding my x, 1, 2, and 3. So I get negative 2x2 plus x3, x2, x3. So if I factor out an x2, if I factor out an x3, okay. So for lambda equal 1, my eigenvectors are negative 2, 1, 0, and 1, 0, 1. Okay, so to be diagonalizable means I can take my matrix A, right? This is my A. This is A. So A should be equal to P, D, P inverse. So since this is 3 by 3, all of these need to be 3 by 3 matrices, right? Okay, so let's make up the D and the P at the same time. So I'm going to put on the diagonal, the lambda is 5, and so that means on my P matrix, I've got to put the corresponding eigenvector there. So this is a diagonal matrix. So then on these two, I need to put the eigenvalue of 1. So I put the eigenvalue of 1 on those two entries, and then I'm going to put these two eigenvectors. So the order of these eigenvectors does not matter. I could switch the order. It's not, P and D are not unique, but this works. So a matrix A is called diagonalizable if I can make up the P and the D. So that means I might have I only have 2 eigenvalues, but I have to have 3 eigenvectors, and they'll be linearly independent, and that makes P, and that's invertible if it's linearly independent, right? So I'd have to be able to find 3 eigenvectors for a 3 by 3 matrix.